get back to ether, discussions regarding ether. This is the experiment that put the United States on the map. United States in physics was kind of like United States in soccer today. Not much was happening here in the United States up until Michelson and Morley decided to conduct the following experiment.
There are only a handful of experiments in physics that completely transformed physics. At many people's top of the list would have to be the Michelson-Morley experiment.
In the 19th century, physicists thought that since sound waves travel through air, light waves must travel through some sort of medium as well. They called this theoretical medium ether.
The famous luminiferous ether, this magical medium that was hypothesized to be what light required to move through the vacuum of space, just the way sound requires air to move from one place to another. How else could waves of light move through the vacuum of space unless there was some medium there, some hypothetical medium? Let's call it the ether.
Ether, they theorized, is an invisible nothingness that permeates the universe. Its only physical property is that it allows light to propagate through it. But once precise measurements of the speed of light became possible, testing the predicted effects of ether on the speed of light became possible as well. The Earth orbits the Sun at about 66,500 miles per hour. If light travels through ether, they reason, then as the Earth moves through the ether, the speed of light should be different going with the ether than perpendicular to it. In an attempt to show the effects of ether on the speed of light, Albert Michelson and Edward Morley conducted an experiment in 1887 at what is now Case Western Reserve University.
Michelson was an expert in optical experiments, and he thought that he could devise an experiment where one would be able to see the slight difference in the speed of light measured on the Earth if you measured it along the direction of the motion of the Earth and at right angles to it. There should be a slight difference.
Compared to the speed of light, Earth is not moving that fast. So if you're going to check the difference in the speed of light measured with the movement of the Earth compared with transverse to it, you need a level of precision that no one had before. The Michelson interferometer was just such an apparatus.
Michelson and Morley devised an apparatus that would detect minute differences in speed between two beams of light. Light from one source is split into two directions through a half-silvered mirror. These beams are bounced between other mirrors and then recombined back into a single beam. When two light beams combine, if their waves are completely synchronized, the peaks combine to make an even more intense peak. If they are one half wavelength off, their peaks combine and cancel out the intensity. Slight differences in speed between two light waves will therefore produce a pattern based on the amount of interference between the two beams. This is known as an interference pattern. Examining the interference pattern from the two light beams sent out in different directions would clearly show if the speed of each light beam were different in different directions. But Michelson and Morley never detected such a difference. Their results were inconsistent with the existence of ether.
The scientific world didn't know what to make of it. The famous scientists in Europe, all Lord Rayleigh and Lord Kelvin and Lord Thomson, were saying, hey, come on, you must have done something wrong here. There has to be an ether. And the whole thing didn't get resolved until many, many years later when Einstein came along.
Einstein's theory of special relativity proposed that the speed of light is always the same, regardless of the speed of the light source. The results of the Michelson-Morley experiment were entirely consistent with Einstein's view of the universe, and this served as the turning point in modern physics.
The Michelson-Morley experiment was an experimental advance in technology that transformed science. Not only physics, but science.
You're muted.
All right, so this is one of the biggest experiments in physics. Also the experiment that put the United States on the map.
1887, the time of Victoria, Queen of England and Empress of
Now
India.
let's take a look at the details of it.
London is the world capital of commerce. Across the Channel in Germany, a child named Albert Einstein celebrates his 8th birthday. It's been 23 years since James Clerk Maxwell stated his equations for electromagnetic radiation. Beyond the Atlantic, the Americans have enjoyed more than 2 decades of peace and prosperity since their terrible Civil War drew to a close. Waves of migrants from Europe are swelling the population of the United States. The western frontier is being settled and settling down. Looking back, 1887 seems like a time of tranquility, not only in commerce and politics, but also in science. Many physicists believed that all the great discoveries had been made. Physics had reached a state of perfection that was positively ethereal. In fact, the concept of the ether was one of its central tenets. And in 1887, in Cleveland, Ohio, 2 physicists, Albert Abraham Michelson and Edward W. Morley, were preparing an experiment designed to prove once and for all that the ether really existed. Certainly, the ether really had existed, at least in the minds of philosophers, for thousands of years. Today, we can readily accept the idea of space as a vacuum, vast stretches of the cosmos that are virtually devoid of matter. But to the ancients, the concept of a perfect void was impossible to grasp. Space had to be filled with something, they thought, and the solution that Aristotle devised was the ether. That was the substance that filled what would otherwise be empty space. And by the 19th century, the ether had come to serve more than a merely philosophical need. The ether was the medium through which light waves from the sun would propagate to nourish and illuminate the earth. Waves can propagate along the surface of water, or through the body of a crystal, or through the air of a concert hall. But any wave is a disturbance that passes through a medium from one part to another on down the line. In other words, whenever there's a wave, something must be waving. But when light waves from the sun reach the earth through apparently empty space, what's waving? In the 19th century, the answer was as clear as space itself. It was the ether. To 19th century physicists, the ether was not only real, it had physical properties that could be deduced by observing its behavior. For example, the speed of any wave depends on the stiffness of the medium through which it passes. And of course, the speed of light is enormous. So, the ether must be very stiff indeed. In fact, physicists said, it was nearly impossible to compress it at all. On the other hand, the Earth and other planets moved through the incompressible ether with perfect ease, obeying Newton's laws as if they weren't passing through any medium at all. If the ether behaved like a viscous fluid, the orbiting planets would gradually lose energy and spiral inward towards the sun. And since that certainly didn't seem to be happening, physicists were able to reach another definite conclusion about the ether. The ether, they said, was a perfectly mobile fluid with no viscosity at all. It was a transparent, perfectly non-viscous, incompressible fluid that filled all of space. Knowing so much about it, the only job that remained was to demonstrate its existence directly in a clear and irrefutable experiment. Somehow, that job had eluded the grasp of physicists throughout the century.
Okay, so the planets. So how do we detect these planets, given the fact that because of the glare, the bright glare from the stars, make it impossible to see these planets directly? All right, so there are a number of ways of doing it the way we used to do it. Up until 20 years ago, or up until recently, let's say, taking advantage of the action and reaction law. Action forces acting on the moon. So that extends all the way up to the moon. And the reaction force is acting back on the Earth. So as the moon is going about the Earth makes a small counterorbit. Imagine that the Earth is the star, and the moon becomes a planet moving about it. You can see the star, but you cannot see the planet. So what's going to happen is the star starts to move towards and away from the telescope. It's moving towards the telescope. There's going to be a shift in color of light. This is known as relativistic Doppler shift. So it's going to shift towards the blue end of the spectrum. And as the star is moving away from the Earth, there's going to be a shift in color towards the red end. So it's going to experience that relativistic Doppler shift.
When she sees the speed of a star change with a clear rhythm, she'll know the star has an orbiting planet. Just as two rollerbladers spin around each other, a planet and its star are in mutual orbit. Gravity works in both directions, so that even a small object like a planet will cause a much larger object like a star to wobble. Such a wobble in a distant star would be indirect evidence of a planet. But how do you see the wobble of a star? Just a sound rises in pitch as its source travels toward us. And drops as it moves away. So light shifts in color as the star wobbles. For years, Fisher and her collaborators have been looking at a star called Gliese 876. The star's color has been shifting. Fisher is hopeful she's seeing a wobble caused by a planet, but she isn't yet convinced. Fisher isn't the only researcher to look for rhythmic star motion. In 1994, another team was searching the constellation Pegasus. Back then, no one had ever found a planet around a distant shining star. Astronomer Didier Queloz thought he saw a star wobbling because of a planet. If Queloz was wrong, his credibility and his young career might be destroyed.
I realized that it was highly risky if the data turned out to be wrong and a mistake. It would have been very bad for me.
The technical challenges were reason enough for caution. Earth zooms through space, but stars move slowly.
It's as if you were in a rocket and trying to monitor the speed of ants on the ground.
Pilot had to figure out what his measurements meant. He first convinced himself he wasn't seeing sunspots on his star, called 51 Peg, rather than star motion. He next made sure the star wasn't quivering like a serving of cosmic jello, rather than moving back and forth. Finally, Queloz knew what 51 Peg wasn't. Now he had to take the leap to say what it was. Didier Queloz's star was wobbling. After careful study, only one explanation made sense. An unseen planet must be moving 51 Peg. Queloz had discovered the first planet orbiting a distant shining star, but others were skeptical.
When we announced 51 Peg, I think that maybe only 10% of people believe we have the planet.
Scientists never thought such a world could exist. It was a planet 140 times the mass of Earth, and it wasn't supposed to orbit this close to its star, according to planetary theory. Queloz's world is an unlikely sight for life. It whips around 51 Peg every 4 days. The temperature is 1,500 degrees Fahrenheit, so hot that the metal nickel vaporizes, perhaps adding a blue glow to the fiery atmosphere. After Didier Queloz's discovery, other planet hunters knew they were on the right track. Now more than ever, Deborah Fisher and co-workers were eager to find their own world. If her star is really wobbling because of a planet, she should be able to predict the star's next move. Fisher began with the star speeds she had measured. She then used these measurements to make predictions of what her star would do next. As she observed her star again on a series of nights, each of her predictions came true. Deborah Fisher had found her first planet.
It's a very powerful feeling to make a prediction and have the star obey my, my command.
Fisher's planet is a ball of gas nearly 700 times the mass of Earth. Her planet swings in a wild orbit that takes it from burning proximity to the star to a freezing distance. Angel's novel two-eyed telescope may be the first to analyze directly the faint
All right, so we go from that method
light
to
of an alien planet.
the binocular telescopes. How do they work?
The two mirrors will be yoked together to create history's biggest pair of binoculars. Each mirror will have a slightly different view of the star. The light waves from these two vantage points will be combined to reveal a distant planet's light.
Well, the difficulty with trying to see planets around stars is that they can be 1 million or even 1 billion times fainter than a star. So any kind of glare from the star spoils your view of the planet. There's a trick to get rid of the starlight and leave the planet light there. And what you can do is combine the waves from the two mirrors so that the crests from the wave from one mirror come at the same time as the troughs from the other. When you add those together, the starlight cancels. So in that way, you can make the star thousands or tens of thousands of times fainter and leave the planet so you can detect it.
All right, so by using two mirrors, you can try to cause a destructive interference pattern, thereby just vanishing the star and making the planet visible. Soap bubble. Notice that we have all sorts of iridescence on top of it, so we end up seeing different colors. What's causing these different colors on the soap bubbles? This is known as the thin film interference. Fresnel is a French physicist who's responsible for the explanation of it. Now, what's causing it to happen is the thin film that we may have. So this is going to be the thickness of the film that we're looking at. All right, so we got the air, we got some kind of gasoline on top of water, and this gasoline, the thickness of it is going to be extremely small. And imagine that the light is coming at a very small angle. So this is the incident light. Part of it is going to get reflected, part of it is going to get refracted, so the light is going to split. Refracted ray is going to get reflected again within the gasoline, and then it gets refracted again. And there's going to be an interference between the first reflected and the second refracted. So that interference could be destructive. It could be constructive, which means that certain colors will pop out, and it could be destructive in the sense that certain colors will just vanish within the thickness of this thin film that we're looking at. All right, so in order to set up the mathematics, what we need to do is go back to some of the rules that we learned from physics. If the wave is coming from a less dense into a more dense medium, upon reflection, it's going to get inverted. All right, so incoming ray, this is less dense, this is more dense. If it's coming from a less dense medium into a more dense medium, upon reflection, it's going to get inverted. Transmitted pulse is going to be upright. It's going to have the same measure. So instead of light is coming in, index of refraction of gasoline is larger, which implies that it's going to be denser. So upon reflection, this is going to be inverted. And then the wave that passes through is going to have the same phase as the incoming one, so there's no inversion. And then it's going to get through the material, so there's no inversion in this one, so it's going to hit this medium. All right, so this one gets inverted and this is not. So these two waves will be out of phase with respect to each other. All right, so